right, let's continue on with part 2 of computer math operations.
Okay, the 2's complement. Not to be confused with a complement, but the 2's complement is how we're going to handle this problem of negative numbers. And so when we first start thinking about positive and negative numbers, if I gave you 8 bits, you know that that is a range of 256 possible values from 0 to 255. And if we said that they were all positive, well, that means that the entire set of 8 bits would be used for magnitude. But if I said you've got to represent positive and negative numbers in there, well, you might say, okay, well, we'll divide the space in half and we'll have 128 negative numbers and 128 positive numbers. And then I might say, well, how would you represent 0? 0's got to be in there somewhere too, and is 0 positive or negative? So we actually have to come up with a little bit different way of dealing with that. And so normally the way that we think of positive and negative numbers in a set of 8 bits is with the formula that you see there. Negative 2 to the n minus 1, all the way down to 0, and then to positive 2 to the n minus 1, minus 1. Well, what's n in this case? Well, n is the number of bits, so it's 8. So this would be negative 2 to the 7th, all the way down to 0, to positive 2 to the 7th minus 1. And so the range of possible values is negative 128 to 0, and then all the way up to 127. Now, in the case of these values, if you took all the values from 1 to 127, what you would realize is that the high order bit, the most significant bit, the one on the left, would be 0. And so in that case, all of the positive integers would have a 0 in that high order bit. In the case of the values from 128 to 255, right, all of those have a 1 in the high order bit. So another way to look at that is we could just say that that 1 is a negative indicator, right? Just means that all of those numbers are 1. And then instead of having a range of 128 to 255, we just say, oh, those are all the negative numbers from negative 1 to negative 128. And so that's how it works. Now, a part of adding these values together, right? So now that we've got our hands wrapped around how we represent negative numbers given a set of binary digits, how do we do the 2's complement? Well, what we have to remember is that there's 2 rules that we have to deal with. One is the reflection, and that's really just converting all the 1's to 0's and all the 0's to 1. And then we have to add 1. So if I was going to take a look at this value here, so I've got this binary number here. And I've already told you that if you got that high order bit is a 1, then that makes it a negative number. Well, how do we tell what the negative number is? So if I take away that 1, you might be tempted to say, oh, that looks a lot like 31. But it's not. It's actually negative 97. Well, how in the world did I get that? Well, what we did was reflect them all, and then we add 1. So don't be fooled by the number of bits that I use. So I'm excluding the high order bit here. So I'm just reflecting the first 7 bits. And so we start off with 0, 0, 1, 1, 1, 1, 1, and we wind up with 1, 1, 0, 0, 0, 0, 0. And then we add 1 and we wind up with 1, 1, 0, 0, 0, 0, 1. And that value comes out to be 97. And so that's how we would determine what number we're actually talking about. So let's first take something fairly straightforward, and we will say if I go from a 1 to a negative 1, what does that actually look like? Well, we start with an n-bit representation of the integer. So if we're talking about an 8-bit system, that's what 1 looks like in binary, 0, 0, 0, 0, 0, 0, 0, 1. And then we reflect all of the bits, and then we add 1. So now we wind up with the pattern 1, 1, 1, 1, 1, 1, 1, 1. And normally you might say, oh, that's 255, but it's not. It's -1. And so there's you can't just look at a negative number and then do the binary calculation and determine what it is. You have to realize that this is actually a negative representation of the value. Now, you don't even have to believe me. You can take a look at what our handy dandy Windows calculator does. So if we put in a 1 and we look at the binary, we can see that it's 0001. But then we convert it to -1, and all of a sudden Windows flips out, right? And we see that we've got that binary value down there. Holy cats. So that's what shifting to negative does. And the way that we got there is with the 2's complement negation. So let's do another example real quick. 6 to -6, it's the same idea, right? We take however many bits we're using to represent the number, we flip them, and then we add 1. And so that's what a -6 looks like, and we can see that our Windows calculator does the exact same thing. So how does this get applied to addition, and how do we handle negative numbers in that case, or adding negative numbers? How does this actually work? Well, let's start with a really simple problem like 9 minus 14. And we know that this is going to wind up with a -5 at the output. And so one way to think of subtraction is not really subtracting numbers, right? Because we're talking about this in the context of adding. So what we're going to do instead is add a negative number. And let's see how that works. Okay, so we have our two numbers to begin with. And we say we're going to convert the 9 to binary, and we're going to convert the 14 to binary. But then we're going to take the 14, and we're going to reflect it and add 1, and then add the two numbers together. Now we know that we're looking at -5, and so when we look at this value when we're all done, we know that that high order bit, that 1 there, indicates a negative number. And if you throw -5 into your calculator, or you just do the problem, you'll get that value there. So we know we have the correct value when we have the same carry in as the carry out, or the two are the same. But for our examples, all we really need to worry about is whether or not we understand why we got a negative number and then how to represent the negative number. So let's do another example of subtraction. Remember that when we're subtracting, we're not really subtracting. We're going to add a negative number. And so 49 minus 27. Well, we can't really do that. So let's take 49 and add a -27. So again, we reflect and we add 1. So when we have it rewritten, we wind up with the result there on the bottom. So we know that we're looking for 22. In this binary case, we get 16 plus 4 plus 2, which is, of course, 22. All right, let's do something a little more challenging. 216 minus 239. We know that this is going to result in not only a negative number, but we also know that this is a subtraction problem. So let's write it in binary, and then we will reflect and add 1 to the lower number, right, our lower add end, and then we'll rewrite it. And we get 11101,001. Well, it turns out that that is -23. And the way that we would check would be converting back to see if we get 23. And so we would invert again and add 1, and it turns out that we get 23. How about that? So that's the way that it works. And just to be sure, right, we can check it out on our handy dandy calculator, and there it is on the right hand side. So here's something fun to think about. If we took a base 10 number and we thought about all the different ways that we could write it, right? We could write it based on its component parts, 40 plus 5 plus 0.6 plus 0.07 plus 0.008. We could write it in scientific notation, but then we would notice that all of the numbers to the right of the decimal point would have negative exponents. And we know that negative exponents are fractions. So we could say that 6 times 10 to the minus 1 is actually 6 divided by 10. And 7 times 10 to the -2 is 7 over 100, and so on and so on. So what if we had a binary number that used decimals? Well, we could look at it the same way. We just have to recognize that we have a completely different base from which to work. And so if we move to the left in a binary number, we know that we're doubling. We also know that if we move to the right in a binary number, we're cutting things in half. So if we take the same idea, we know that numbers to the right in binary could be written as sort of fractions as well. So in this particular example, we would say that this is 1 times 2 to the first plus 0 times 2 to the 0 plus 1/2 plus 1/4 plus 1/8 and so on. So this value of 10.111 is actually 2.875. So what really happened in the denominator of the numbers to the right of the decimal point was that we just had an increasing power of 2, which of course makes the number smaller and smaller and smaller. And we could actually represent all of this in scientific notation in the same way that we did above for a base 10 number. And this brings us to floating point numbers. The minute we have one of those fractional values, then we have to realize that we have a whole different thing that we have to figure out. So decimals and fractions, we need a new structure to represent those values. We can't just write simple binary numbers anymore. So how do we represent something that's an exponent or a decimal or a fraction in binary? Well, it turns out that there's actually a standard that tells us all how to do this. So IEEE 574 is floating point arithmetic. And so we'll just read. The standard specifies the interchange and arithmetic formats and methods for binary and decimal floating point arithmetic in computer programming environments. So the details and the standardized way of doing it are all right there in IEEE 574. But there's a couple of things that we have to think about. Right, if we really want to sort of understand this, or at least understand that there's a structure out there. The first thing is that we're dealing with this exponent or decimal or something like that. And there's a term that we use to refer to part of our number, and that is the mantissa. So in the red here, 3.4, that's the mantissa. And then we've got this exponent that we have to deal with. So we've got to have some way to tell the system how big the number is. And then we got to tell the system what the exponent actually is, right? And then we've got to determine whether or not it's positive or negative. So let's take a look at the little graphic up top there. That first bit, the one labeled S or colored in red, that is for the sign, and that works the exact same way that we've talked about before. The yellow E's are for the exponent value. And then the rest of the value is for the mantissa. Now we've also got in programming, when you're trying to decide how much precision you want to add to your system, that is how accurate you want to be, or how much memory you want to allocate to my variables, you can pick whether or not they're single or doubles. And a single precision value is 32 bits. And so that's what's represented up above. But you can provide a lot more precision. It takes more memory to do that. It takes more space. So you can use doubles. And these are 64 bits commonly. And then there are a couple of other structures as well. So the value of the exponent changes depending on whether or not you're a single or a double. Same with the space allocated to the mantissa. Now, without being too crazy here, because the video is actually getting quite long, there are some crazy calculations that go on inside a floating point number. So for example, the exponent is not actually represented directly, right? There's a bias of 127 and so on and so on. If you really want to see an example of how this calculation is actually done, you can go to that URL down there, or you can just Google how our floating point number is actually configured, because that's a little more than we want to do here. Well, thanks for watching. Thanks for listening. I hope that your calculations always come out the way that they ought to, and may your packets always reach their destinations too.